Okay, shall we start again? So it's a pleasure to have Nikita Nikolaev from the University of Sheffield talking about Abelianisation and the exact WKB method for meromorphic H connections. Thanks.
Okay, thanks. I'm very happy to speak. Awesome conference. So this was delayed by a year. I'm actually to be honest, I'm kind of glad actually that it was delayed by a year. I lucked out because I think if I gave this talk last year, I wouldn't have been able to tell you about maybe half the things that I would like to tell you, or maybe or at least not with the same amount of confidence. So right, okay. So let me just jump right into it. So I'll fix throughout the whole talk a compact Riemann surface with a divisor. A divisor could have high multiplicity, and whatever, it has to be non-empty. And if I'm on P1, it should be degree at least 3, etc. And so I'll be studying meromorphic H-bar connections on this Riemann surface X, which is to say that these are H-bar families of meromorphic connections. So I better, I'll cross my Riemann surface X with H-bar space. So technically, H-bar connections are they're connections on this X cross H-bar space, and you should define them as relative connections, etc. But let me just give you kind of a working definition, which will be enough to understand everything. So a meromorphic H-bar connection, E nabla, on this pair XD. So that's a pair of, so it's a vector bundle on this X cross H-bar space, together with a map nabla on sections of E. So just the usual, it looks like the usual connection, except that the Leibniz rule for this connection is twisted by this parameter h bar that I've introduced. And the way it twists the Leibniz rule is in a very specific way by introducing h bar in front of the de Rham differential that's applied to the function. So this is the only nonlinear part in the connection. This is what makes this map a differential operator rather than an endomorphism. Well, okay, so there's the last condition is that it has to behave well as I go into h bar goes to 0. So okay, so let me explain a little bit more about this definition. So first of all, I said C sub h bar linear map. So by that I just mean that this map is linear. It's a homomorphism when it comes to functions of h bar only. So differentiation is only in the x direction. And this Leibniz rule, this twisted Leibniz rule, means that if I write down my connection locally, then it looks like maybe a more familiar expression, which is that you have the de Rham differential multiplied by this parameter h bar plus some endomorphism, which in principle could depend on h bar. And to be even more concrete, these things are like differential operators, so systems of linear differential equations which are singularly perturbed. So the differentiation has this parameter h bar, of which we think as small. And so then there is this additional technical thing, which is that I'm going to describe a certain correspondence for these connections, and the behavior of this correspondence turns out to be very transcendental in h bar. The way it depends on h bar is very transcendental, and in fact, it's so even if I start with connections, so I'll be working with rank 2 connections. If I start with connections which have a very mild behavior on h bar, something like algebraic or something, then this correspondence is only going to be defined in certain sectors in the h bar plane. So when I say h bar space, I really kind of implicitly I am picturing working in some kind of sectorial domain like this, where the radius of that sectorial domain I'm not fixing. So it's really a germ of these things. And then when you restrict, when you consider such more general behavior of connections with respect to h bar, then it really it makes sense to be more precise about what you mean, behaves well as h bar goes to 0. So in the ordinary situation where this thing is well defined over the entire complex plane, that just means that whatever, I can restrict my connection with a vector bundle to this central fiber at h bar equal to 0, and everything's fine. It depends on h bar holomorphically. But in my case, things do not have to depend on h bar holomorphically. In fact, they won't depend on h bar holomorphically. Instead, they have to be holomorphic in sectorial domains like this. And the condition that you want to assume is some restriction on the asymptotic behavior as I let h bar goes to 0 inside this domain. So this is a kind of a technical point. And the reason you need to worry about this is because the correspondence that I'm going to explain, its dependence on h bar is this complicated kind of transcendental sectorial thing. So in order to set up the correspondence, you kind of need to allow many more connections into your category, or allow much more general behavior on h bar. And so that's so that's why it may look a little bit complicated. The precise the correct words to use in terms of what kind of regularity on the asymptotics I want to require is Gevrey asymptotics. So I will try to de-emphasize these aspects because they're quite technical. But just keep that in mind that the behavior is quite complicated in the h bar direction. Okay. So an example. So probably the example that you're most familiar with is the Schrödinger equation. So if you look at this differential operator, so that's a second order differential operator. You can see there's an h bar in front of the derivative. And of course we have the potential, which is a function, literally a function now, function of x, and in principle also a function of h bar. And so the way you go from these differential operators to connections, which is what I'm studying, is by applying the so-called jet construction. If you've never heard those words before, I can guarantee you that you've actually applied jet functors in your undergrad studies when you convert a linear differential equation into a system of differential equations by, you have a differential equation of f, and then you kind of introduce these auxiliary variables where you call f prime the new variable, f double prime the new variable, and so on, and then you write this as a system. That's the jet functor. And so if you do this in this case, then the connection that you write down looks like this system. So you have this. So this is a rank 2 connection, and the matrix looks like this very typical off diagonal matrix. And the bundle is the so-called one jet bundle. So right. So I'll kind of periodically make these remarks regarding the h bar asymptotics because they are important, but maybe they're just a little bit too technical. So in this particular example, so what I was talking about, these Gevrey things, is that so in this particular example, my connection, the data of the connection is essentially just this function q, a function of two variables x and h bar. And so the typical situation that you would encounter is that q is, well, the most typical situation you would encounter is that q is just independent of h bar. It's just a function of x. But more generally, you could think that it's some kind of polynomial in h bar. But yeah, so in order to set up the correspondence, the space of such things that you need to allow, the dependence of q is more general than that. So q would be a function of h bar in this some kind of sectorial domain. It is not assumed to be holomorphic at h bar equal to 0. The only thing you assume is that it admits asymptotics as h bar goes to 0. It admits an asymptotic expansion, and then you want that asymptotic expansion to be of a certain regularity, which is called Gevrey. Right. Okay. So h bar connections, of course, have this central fiber h bar equal to 0, which is a really, really important feature of these families of connections. If you recall the the Leibniz rule, the way h bar enters the Leibniz rule is that if I literally set h bar equal to 0, then it kills the nonlinear term, the differentiation term. And so what remains is an endomorphism. And that is a Higgs field associated with your h bar connection. So I'll denote that by straight E and phi. So any given an h bar connection, you always, by taking the limit as h bar goes to 0, you get a Higgs bundle. So I call that a limiting Higgs bundle. It's a meromorphic Higgs bundle. You know, again, in the previous example with the Schrödinger equation, this limiting Higgs field is just the matrix in the connection, except that I also, you know, I only take the leading order part of the potential Q. So that's my Higgs field. Okay, so and of course the cool thing about Higgs bundles is that there's an amazing correspondence that you can study with Higgs bundles, which is that you rewrite it as a certain abelian data on a covering space. So that's called the spectral correspondence. And the way, I'll just remind you the way it goes. It goes as roughly like this. So I have this vector bundle E now with an endomorphism. So I take the characteristic polynomial of the endomorphism. And that gives me a bunch of differentials, abelian differential, quadratic differential, cubic differential, etc. And you write down the characteristic polynomial that gives you a section of a certain bundle on the total space of the cotangent bundle, and you take the zero locus of that section, and that traces out a curve, which I call sigma, which is called spectral curve. It's an algebraic curve inside the total space of the cotangent bundle, with a slight twist here because everything is meromorphic. Normally, the places where the eigenvalues of the Higgs field blow up, so just around the poles, the spectral curve would kind of escape the total space of the cotangent bundle. So what I want to do is I just want to modify those fibers, basically blow down, blow up, such that my spectral curve remains the same. It remains inside the total space, and I kind of record exactly the rate at which they approach, you know, what would have been the kind of line at infinity in the ordinary cotangent bundle. So this is called a twisted cotangent bundle. And so you get this nice covering Riemann surface above the entire Riemann surface X. Everything is compact. It's a ramified covering. Its rank, the degree of this covering is the same as the degree of the vector bundle E. So again, here's an example. The previous example when I had the Schrödinger equation, so that was a second order ODE, which I've converted into a rank 2 H-bar connection. So then I took the limit of that, and I had a rank 2 Higgs bundle. And so the corresponding spectral curve is a 2-to-1 covering. It's a double cover of X, which is literally, in this case, works out to be, you know, the Riemann surface of square roots of Q naught. Okay, here's an image to go along with it. So green, this is my spectral curve, literally cut out by an equation that looks kind of like this. This blue fiber here, that's the fiber that's been modified from the usual cotangent bundle. So normally if I constructed this spectral curve inside the usual cotangent bundle, then it would kind of go off to infinity like this and escape. But I want to kind of cap this off so that the thing remains inside my my bundle. And in particular, you see that, I've very suggestively drawn that I want my curve to be trivial above the divisor D, so that all my singular points where I'll allow my connections to allow singularities, they always have precisely 2 preimages. There's no ramification above them. And this is going to be part of my assumptions. Right. Okay. So that's one thing that you can extract out of a Higgs bundle. So those are the eigenvalues. But of course, we know from linear algebra there's also eigenvectors. So I'm going to keep track of those. Well, that is also a very simple thing. So just pictorially, if this is the curve of eigenvalues, we know that to each eigenvalue there's an eigenvector. So if I just plot attach the line of eigenvectors to each point on the curve sigma, then I get a line bundle over sigma, and that's the spectral line bundle. So I call that straight L. Right, that's what I write here. This is a line bundle of eigenspaces of phi. And okay, the more correct definition of L is that you take your endomorphism phi from the base, you pull it up, you pull up the bundle and the endomorphism phi. Now you have some kind of endomorphism of a bundle on sigma, and then you look at the kernel of this endomorphism, where lambda is the canonical one form, which is or sometimes called the Liouville one form or the tautological one form. The physicists know it as PDQ. So that thing exists on the cotangent bundle, but it also exists on this twisted cotangent bundle, except that this time it's meromorphic on the fibers that have been modified. So what I get is a and then of course I can restrict it to the spectral curve sigma, and I get a meromorphic one form on the spectral curve sigma with poles precisely along this pullback divisor. Okay, and so basically I started with a Higgs bundle E phi. I've extracted the spectral curve sigma, and I've put a spectral line bundle L on sigma, and there's also this canonical one form flying around. And the cool thing is that this procedure is kind of invertible. It's a correspondence. So one way to state it is that I can get back my original vector bundle with the Higgs field by push forward. So I take L, this is my line bundle on sigma, and I push that forward. That's a rank 2. So I'm pushing down degree 2 covering. That's a rank 2 vector bundle. That equals E. And then this canonical one form, I'm going to think of this as like a rank 1 Higgs field on my line bundle, just because it's a one form, so I can multiply sections of L by this one form. So I get this lambda induces a map for me from L, or it's an endomorphism of L valued in differential one forms. And so if I take that endomorphism L, lambda on L, and I push that forward, that equals phi. So this equality, you can think of it. So I mean, it's called spectral correspondence. But when I phrased it this way, with this lambda being an abelian or rank 1 Higgs field, you can think of this as a kind of abelianization of Higgs bundles. That I started with a rank 2, or more generally rank n Higgs bundle, which is a non-abelian thing, and I've somehow expressed it equivalently in terms of some abelian object, but on a covering space. And of course, the idea of abelianization is very much it's very much the same idea, and I could say that this slide is kind of an analogy to abelianization of connections. But actually, I think one of the main points of the talk is that it's much more than an analogy. So I'll try to explain that.
Okay, sorry, so I have a bit of a question about this. Is it clear that this line bundle is well behaved? Well, it's well behaved as a line bundle at the ramification points?
It is not completely clear. You have to do a little bit of work. The best way to do it probably is to think of L as a sheaf of modules, and then you can just show that it's locally free of rank 1. This is literally would be the definition. This is your sheaf, and you can show that it's locally free of rank 1. That requires that your spectral curve is smooth, non-singular. Of course, it is a zero locus of a of a section, and the zero locus could have singularities. So when you have singularities, you can still build this. The problem then with that, it wouldn't be a line bundle anymore. It would be just a torsion-free sheaf. But yeah, it's not obvious from what I said, but you can check it.
Okay, thanks.
Okay, so what about connections? So here's the kind of main result that I want to explain. So it's called H-bar Abelianization. So what I'll do is I'll fix a spectral data. So it's going to be a spectral double cover sigma with the assumptions that the ramification is simple and that the branch locus on X is disjoint from the places where I allow my connections to develop singularities. And then the theorem is goes like this. So if I fix a generic phase theta, then there is an equivalence of categories. And the categories are like this. So on the left, I have rank 2 H-bar connections on this pair XD, with limiting spectral data being this sigma that I fixed. So that's on the left. And on the right, I have rank 1 H-bar connections on the spectral curve sigma with poles along the pulled back divisor. And by the way, this is pulled back as a divisor, which means I'm pulling back the multiplicities themselves as well. So these connections are meromorphic along the pulled back divisor, but also along the ramification locus with specific, the residue works out to be specifically -1/2 for some reason. Well, okay, and these are H-bar connections, so I should tell you what their spectral data is. Of course, they are rank 1, so there's not much to say apart from the fact that the limiting spectral data is just the canonical one form. Okay, and so there's a functor like this, and it turns out to be an equivalence of categories. And what's more is that it fits into the following really cool diagram, the diagram that I really, really like, which goes as follows. So suppose I start with one of these rank 2 H-bar connections, E nabla. So now there's kind of two things that I can do to it. One, which is the more standard thing, which is that, well, it is an H-bar connection, so I can take the limit as H-bar goes to 0 and look at the corresponding limiting Higgs bundle and apply the spectral correspondence to put a line bundle with a rank 1 Higgs field on it over the spectral curve. So okay, so that's traditional. But now there's a new thing that I can do, which is that before taking the limit as H-bar goes to 0, I can abelianize this thing in H-bar families, and what I get is a rank 1 H-bar connection on the spectral curve. And of course, it is an H-bar connection, so I can consider its limit as H-bar goes to 0. And then the theorem is that its limit is exactly the spectral line bundle with the abelian Higgs field. So this is a really cool commutative diagram. Okay, one thing you could take away is that I said the inverse of the spectral correspondence is the push forward. Is just the push forward functor. So then the inverse of this equivalence of categories, which there is a canonical. I'll explain why there is a canonical inverse equivalence. So that's some kind of functor going in the opposite direction, and you can take the it depends on H-bar because everything is in H-bar families. So you take the limit as H-bar goes to 0 of that, whatever that functor is, the H-bar non-abelianization, and the limit is precisely just the push forward functor, just because the push forward functor is the thing that inverts this arrow. Okay, so basically for the rest of the talk, I want to try to explain how one could arrive at these statements, what goes into this. So let me make a couple of remarks first. So first of all, I've already kind of mentioned it, but it's just important to emphasize that these line bundles, L del, that you get through this correspondence, they're generically not holomorphic at H-bar equal to 0. So even if, as I said, my connection E nabla was like algebraic in H bar, generically, so if my connection were something like nabla H bar D plus phi, where phi is independent of H bar, like as something as simple as this, generically abelianizing this thing, the abelianized connection is going to be not holomorphic at H bar equal to 0. But it's going to be defined in these kind of sectorial domains, with opening being a half plane, bisected by this generic phase that I've picked, theta. And they have well-defined asymptotics, so it still makes sense to take limits. Of course, you need to what does it mean to take a limit of a line bundle or a vector bundle, etc. You need to define all this, but you can make sense of all this. Okay, so that's remark number one. Remark number two is that because of this limiting feature to the spectral line bundle with the canonical one form, you could say that it has this abelianization connection has this really, really attractive expression. So everywhere on sigma, and I do mean everywhere, there's a local generator of L. So that includes over the singularities, over the ramification points. You can always find a generator of L, a local generator of L, in which my connection has this super cool form, which is just the usual H bar the Durham differential plus the H bar independent part, which is the canonical one form, and then something that is of order H bar. And what's important is that this thing that's of order H bar, this beta one form, it admits asymptotics as H bar goes to 0. It may not be holomorphic at H bar equal to 0, but it admits asymptotics, and it's its limit as H bar goes to 0 is well defined. So this thing is of order H bar, and it goes to 0 as H bar goes to 0. So kind of this formula shows you very explicitly why, if I take the limit of these abelian H bar connections, I should get the abelian Higgs field on the spectral curve. Okay, the reason this formula is kind of cool is because, well, this is a rank 1 connection, and computing holonomies of rank 1 connections is very simple because it just amounts to integrating and whatever, exponentiating. And having this formula means that if I want to compute the holonomy of this abelianization connection along some cycle of the spectral curve, well, then that literally amounts to computing this number. Well, this is a function of H bar, right? So the leading order part of this function is goes like 1 over H bar times the integral of the canonical one form, which in particular would be or could be a period if gamma is indeed a homology class of the spectral curve, plus some stuff which is of higher order in H bar. And in particular, that gives you a precise description of the asymptotics of the holonomy of this connection. And all this holds again in a half, as H bar goes to 0, in a half plane bisected by this generic phase theta with very nice Givray estimates, etc. And so the reason I mentioned this, I added this slide or this part of the slide yesterday or 2 days ago, based on what Andy said, because these holonomies of the abelianization connection are very, very closely related to these X sub gamma functions that Andy has been describing in his lectures. So in particular, I think I'm hoping that this point 2 kind of answers one of the questions that Andy posed in his lectures, hopefully in full. Okay. Last but not least is that so exact WKB is also in the title of my talk, and the reason is that H bar abelianization somehow contains the exact WKB analysis. Of course, I'm being maybe a little bit I'm being imprecise here because, of course, exact WKB analysis is some kind of vast area. But the specific thing about constructing exact WKB solutions and understanding their properties, that is somehow contained in what I call H bar abelianization. And one way to say it is that it's kind of like if you have a differential operator, singularly perturbed differential operator, you can try to construct its exact WKB solutions using exact WKB analysis. And then what you find out is that these solutions actually give local generators for this abelianization line bundle L, or more precisely, the one jet of these exact WKB solutions that gives local generators of L. Okay, so how could you arrive at this picture? Well, so there's basically three main ingredients in this. So number one is to write down a kind of a more intrinsic formulation of abelianization. Abelianization, of course, was invented by Gayotto Morenitsky in the study of spectral networks. But in order to get this picture of the main result that I'm describing, you kind of need well, I'll give you a slightly different point of view on abelianization, which is a bit more intrinsic in nature. And that seems to be exactly what's needed to proceed. So that's ingredient number one, and ingredient number two is some form of exact perturbation theory, because at the end of the day, we're studying things that depend on this parameter h bar, and eventually we need to be able to solve certain differential equations in a way that keeps track of the behavior as h bar goes to 0. And so that is a subject of singular perturbation theory, and so you need to be careful there. But those two ingredients, actually, they're enough to basically describe what h bar abelianization is. Once you have those two, you get the theorem. And then to relate the WKB method, the exact WKB, to this procedure of h bar abelianization, well, I suppose there's two ways of doing it. One, which is kind of what I already described, which is that you start with a differential operator, you do whatever, you convert it into a connection, you do a h bar abelianization to it, and on the other hand, you solve for exact WKB solutions, whatever, take their jets and try to see if those things match. That's probably perfectly valid. But another way, which I think is kind of cooler, is to really do a kind of a different or reformulation of what it means to apply the WKB method. It's a geometric reformulation. So I'm not, I don't have high hopes that I'll get to this. Maybe I can mention it, but certainly the proof of this part involves all the same ingredients that I would use in order to say what WKB method is geometrically. So okay, we'll see where we get with this. Okay, so let me explain to you my point of view on abelianization. So now let's forget about h bar. So now we're just looking at standard usual connections, no h bar. And what I'll do is I'll just start with a double cover. And I'll assume that it has the right genus and all the same assumptions that I had before, which is that the ramification should be simple and the branch locus is separate from where the singularities are. And so I consider all possible rank 2 connections on this pair XD on the Riemann surface. Again, no h bar, just usual connections. And what I'll fix is local exponents, and I'll fix them to be generic. So local exponents are just, if you take your connection and you restrict it to an irregular point, that you look at the principal part of the connection at that irregular point, and you want to look at the leading order term in that principal part. And so that's going to be some matrix with eigenvalues, lambda 1, lambda 2. Well, technically speaking, these eigenvalues, they're not numbers, they're symmetric powers of tangent vectors. But anyway, we don't have to go in that direction. So you look at those eigenvalues and you want to impose the assumption that the real parts are distinct. So that's what it means to be generic. Right. And so another thing that recall is so what happens at the irregular points with connections. So remember that when you have connections with irregular singularities, the irregular locus gets decorated with certain preferred directions. And so basically, the way you do it is, so for instance, if I look, this is a particular point in my irregular locus. I do the real oriented blow up, so I replace the point with a circle, and that circle has some preferred directions. So in these directions, they always come in pairs, and because of the genericity assumption that I made on the local exponents, there's like a maximal number of them, and they always come in two flavors or two colors. One flavor is, they're called Stokes directions. Those are called kind of points of maximal decay. That's when if you have basically if you have two flat sections of your connection, and you because this is an irregular point, when you parallel transport them, they experience different growth or decay behavior. And so if you look at basically the ratio of these two sections, the difference in the difference in growth rate between these two sections, flat sections, if you parallel transport that into the irregular locus in the direction of a Stokes direction, that means the discrepancy or the difference in how much faster one of the sections grows than the other, that's the direction when that happens to the maximal extent. And as I change the direction of approach, this discrepancy becomes smaller and smaller, and then you encounter these what I call oscillating directions, where you really can't distinguish the two sections simply based on how fast they grow or decay as I go into the pole. And so obviously the way these directions occur, they always kind of occur in alternating fashion, and there's an even number of them. So I'm going to color them in a specific way, which is going to be important. So I'll always denote my Stokes directions with just an empty circle, and oscillating directions with a crossed circle or circled cross. Right. Okay, so now here's the absolute key fact about connections and Stokes directions, which is that if I'm sitting near a simple pole, or if I am sitting near a Stokes direction, so you should imagine, I'm taking like a germ of a sectorial neighborhood of this particular Stokes direction, then this is a classical fact from analysis of ODEs, that my connection E nabla has a canonical flat filtration given by these growth rates that I was just describing a minute ago. So flat just of course I'm studying here rank 2 connections. So filtration really just means an inclusion of a line bundle, a germ of a line bundle. So it's like a one-step filtration. But never mind. The flatness refers to the fact that this L given to me by growth rates, this L, if I restrict my connection to L, then my connection preserves this line bundle. So it sends the sections of L to the sections of L, whatever, twisted by meromorphic differential forms. Okay, so these filtrations, well, they have various names. I usually call them Levelt filtrations. Oops. So the upshot is that you get, not only do you get this kind of restricted connection to one of the filtration pieces, but actually if you take the associated graded of the whole thing, then on the second piece of the associated graded, the connection nabla also induces a flat connection. So what you actually get is a diagonal connection. So you take this filtration, you apply associated graded, you get a diagonal connection. And well, okay, let me skip the next point. The last point is that so these filtrations, the fact that they're flat is very important, because now, although they're defined by some growth condition near these Stokes directions. Because they're flat, I can analytically continue or parallel transport them basically anywhere I want inside my curve X, as long as I avoid the singular locus D. And somehow this is somehow the very first step in abelianization, which is that you realize that you can extract this diagonal abelian data out of my connection. And then the question is, well, okay, can I extend this this description of my meromorphic connection as some kind of diagonal abelian data more globally on the curve? And the answer is kind of yes, because I can parallel transport these associated gradients anywhere I want. But then also you kind of don't know where to parallel transport them. There's like basically an infinite number of choices you need to make. So one way to cut down, or one way to define precisely where I'm supposed to parallel transport these filtrations and which pieces of filtrations and how, is to choose the so-called Stokes graph or spectral network. So now I'll explain how what that is. So I'll define it as a graph, as a bipartite graph on my curve. And so for that, I need to tell you what the vertices are and how I color them. So there's two colors, the same ones that you've seen, the hollow circle and the crossed circle. And so I'll color each simple pole and each Stokes direction with a hollow circle. And then I'll also color each branch point and each oscillating direction with this crossed circle. And so then, the simplest definition of a Stokes graph that I can think of goes like this. So a Stokes graph, or precisely simple saddle-free Stokes graph gamma on this pair XD, adapted to my double cover pi. This is a bipartite square graph. So bipartite means each edge goes always between two different colors. And square graph means that every face is a quadrilateral. So it has precisely 4 edges in the boundary. Okay, so this is a bipartite square graph on my Riemann surface X with the vertex colors as I've introduced them. Those are the 2 vertex colors, together with a choice of orientation double cover on sigma. So sigma is a double cover, and I can lift a graph to sigma. And then there's 2 choices. And that lift I can orient, and I can always orient it in one of 2 ways. So that's the choice of which of the 2 orientations I pick is that's part of my data. And so this graph needs to just satisfy 2 very simple rules. One, which is that at every branch point, so all the crossed circles which are branch points, those need to be trivalent. And then all the oscillating directions, which are colored by the same color, those I require to be bivalent. And in fact, the 2 edges that are incident to it, they have to be the boundary edges on the blow-up circle. And that seems to define the Stokes graph, I think, in a very simple way. So okay, so then the structure that we have is this: we have this square graph, which means all the faces look like these diamonds with precisely 2 polar vertices on the boundary, and 2, well, they could be either boundary, they could be either oscillating directions or branch points. Okay, and the important thing is that these things are kind of simply connected. They're simply connected diamonds. Okay, so what's the point of this? The point is that remember I said that we have these canonical Levelt filtrations near each of these. These could be poles or simple poles or Stokes directions, and so now I have a simply connected domain, and I have 2 filtrations on it. So the natural thing to do is to parallel transport that filtration over the entire square, over the entire diamond. And so now over each diamond, I have exactly 2 filtrations on the same vector bundle. So probably the most natural thing to try to do is to intersect them. And it's a matter of simple linear algebra, which is that if you intersect 2 filtrations which are transverse, that gives you a canonical decomposition of your vector space or vector bundle. And in fact, in fact, what it actually gives you is canonical identifications between your original vector bundle and the associated graded. So I mentioned already, I hope I said that when you have a vector bundle with a filtration, you take the associated graded, the vector bundle is not isomorphic to the associated graded, at least not canonically. But if you have two filtrations which are transverse, they give you canonical isomorphisms with the associated gradeds. So now basically you have, in each diamond, you have canonical comparisons between your original vector bundle and this diagonal thing that you get by taking the associated graded. So I want to do this procedure over each diamond. So the kind of genericity assumption that I'm going to impose is that for each diamond, the corresponding two Livelt filtrations that I get, they are transverse. And then basically after that, you just use all this canonical data that you've extracted simply because you've extracted the Livelt filtrations, parallel transported them to these diamond regions which are given to you by the Stokes graph and intersected them. You now you use the oriented double cover of your Stokes graph to tell you exactly which piece of this associated graded you need to lift to which sheet of the spectral curve. And then you use, again, you continue using these canonical identifications in order to extract canonical gluing maps between the different pieces. And that builds for you a line bundle with connection on the entire spectral curve, sigma. So this procedure is kind of, the way I described it is a very intrinsic, very detailed way of understanding what the Abelianization line bundle, just to give you an example of how detailed it is, I can compute the degree of the Abelianization line bundle, and it works out to be this thing, the degree of E minus the degree of the push forward of structure sheaf, which is some number. And if you've studied spectral correspondence of Higgs bundles, you'll know that the degree of the Higgs bundle E and the degree of the spectral line bundle L are related by precisely this same identity. So everything seems to be matching. Okay, and then so this procedure that I explained, it turns out to be a functor, and in fact, it's an equivalence of categories. And so the theorem is like this. So you have on the left, you have rank 2 connections, meromorphic connections on this pair XD with fixed generic local exponents, which are gamma generic. And then on the right, you have rank 1 meromorphic connections on the spectral curve with poles along the preimage divisor or pullback divisor and ramification. And also, the local exponents are fixed in the same appropriate way, and the residues work out to be -1/2 at the ramification points. Okay, so how do you invert this? So this is kind of this is an important point. Like, why is this an equivalence? Well, the way you proceed is as follows. You so suppose I started with E nabla, so I abelianize it, I get L del, and then I push it forward. So now I have two different vector bundles with connections on the base, E and push forward L. So I compare them. Of course, it's a pair of rank 2 vector bundles on the base. Of course, they are related by a cocycle, obviously. But the point is that because of the way we constructed the line bundle L in this very, very canonical way of keeping track of how it is related to E, that it is these pieces of the associated graded and so on, you can use that to understand that you actually get canonical isomorphisms between E and push forward L over each diamond, just because the push forward L recovers this split structure of the vector bundle E. So you get these canonical isomorphisms. But these canonical isomorphisms, they don't agree as I go from one diamond to another. And so this disagreement, you record it as a cocycle, which is supported on the Stokes graph grammar. Right. Right. So you get this canonical cocycle, and the way I record it as is it's valued in automorphisms of the push forward line bundle. Right. So then there's a key observation about this cocycle V sub gamma. which is that if you, again, if you look at this very precise kind of concrete prescription of how V sub gamma is defined, you realize that it's defined essentially in terms of parallel transport of your abelian connection along certain paths which are canonically determined by the Stokes graph. So in other words, the rule that assigns V gamma to a particular line bundle is always the same. It's kind of completely agnostic when it comes to the line bundle L itself. So this is a kind of interpretation of one of the main observations from the spectral networks paper of Gaeta-Mornitsky, which is what they call the path lifting rule. So I interpret it as being that you have this cocycle which is it's independent. As a rule, it's independent of what the line bundle is that I pick on the spectral curve. And so, so one way to say it is that what you actually get is a cocycle not valued in automorphisms of push forward L, but rather in automorphisms of the push forward of the functor. So I guess the way you could see this this thing is a kind of encoding of the Stokes graph in cohomology. You could ask, how does the Stokes graph help you abelianize a connection? Well, the answer is that you encode the Stokes graph in cohomology, and the cocycle that you get in this cohomology is precisely what acts on your connection in order to abelianize it or non-abelianize it. And so in particular, another way of saying it is that the non-abelianization functor, the inverse equivalence, is a kind of local deformation of the push forward functor. I take a cocycle which is supported on the Stokes graph, and I'm acting with that cocycle on the push forward functor. So so that's upshot number one. I guess another way you can restate this upshot is that abelianization is a kind of local deformation of spectral correspondence, where this local deformation is given by this cocycle V sub gamma. Okay, that's upshot number one. But when it comes to H-bar connections, the upshot is now I think it's clear how you should go about extending abelianization to H-bar connections. If abelianization is really the data of a cocycle, then I need to explain how I would extend this cocycle in the H-bar direction with appropriate behavior in H-bar, which itself, the way this cocycle V gamma was constructed was the main input was these Levelt filtrations and the fact that I was intersecting them. So what you really need to do is construct Levelt filtrations which have good dependence on H-bar. So that's where you get to exact perturbation theory. So I will not. So I'll just tell you what the key technical result is without explaining any details because that would take me too far afield. But basically, what you need is an existence uniqueness theorem for exact solutions of a singularly perturbed Riccati equation. So that's an equation of this form. It's a nonlinear first order ODE. It's singularly perturbed because it has this H bar in front. So I won't explain this, but I give a reference here if you want to see the precise statement. And actually, before I move on, one thing I want to mention is that one cool consequence of this result for the Riccati equation is an existence uniqueness theorem for exact WKB solutions for general second order ODEs of this form. And in particular, if you construct the formal WKB solutions of such an ODE, that it gives you a general condition for when they can be Borel resummed. So this is in my most recent preprint. Okay, so let's see, I have about 7 minutes left. So let me explain how this how you extend the Levelt filtrations in the H-bar world. So these are what I call the WKB filtrations. Okay, so it goes roughly as follows. So okay, so now we've gone back to the H-bar connections. So remember that the thing that we had fixed was a spectral curve with those assumptions on the ramification locus, etc., and the phase theta. So I will extend the spectral curve simply, by crossing it with my H-bar space. So now it's like a spectral surface, I guess, and that's fibered in a 2-to-1 fashion over my X cross H-bar space. Then the next thing I need is a Stokes graph. So the way I, the way I do that is, so I look at the discriminant of the equation that determines my spectral curve. So that gives me a meromorphic quadratic differential on xd. That, as we have already seen in a few talks, that gives, there's a theta horizontal foliation, which has a critical locus, gives you a graph, the critical graph of this foliation, and that's my Stokes graph. And again, I need to extend it in the H-bar space, and I just do it in the stupid way by crossing it with the H-bar space. So kind of now, instead of just having diamonds, I have sort of diamonds cross, whatever my H-bar space is. And then, right, so then there's the key, the absolute key result, which is existence of what replaces Levelt filtrations. So the statement is like this. So if I have any H-bar connection, E nabla, on this X Riemann surface X with a divisor D, with this limiting spectral data sigma, then over each one of these diamonds cross H-bar space, my vector bundle E has precisely 2 necessarily transverse flat filtrations. I call them E1 and E2. And what makes them special is that they have 2 crucial properties. So number 1, which is that if I take the associated graded of each of them, and I look at the limit of that diagonal connection as H-bar goes to 0, then what I get is precisely the eigen decomposition of the Higgs field. And the second property is that if I, well, okay, so these are filtrations, in particular on this entire diamond. If I fix a non-zero value of H-bar with the argument of H-bar being this theta that I fixed earlier, then in particular, I get an actual connection, a usual connection in the usual sense over this diamond, and I can look at its behavior near each one of the poles, and it turns out that this restricted for fixed H-bar filtration, the E1 is the Levelt filtration near this pole, and the other filtration E2 is the Levelt filtration near this pole. So in other words, these WKB filtrations are kind of exactly what you want. They in the one sense they restrict to give you Levelt filtrations near poles, and on the other hand their limit as H-bar goes to 0 is exactly what you want with relation to the Higgs field. They give you exactly the eigen decomposition. So they kind of patch those 2 worlds together in a very nice kind of holomorphic fashion. Okay, let me skip the proof. And basically, right, so this is the theorem that I already stated. Basically, you by continuing this exact procedure that I described before with Abelianization, where you take these Levelt filtrations, right, you extend them over diamonds, you take associated gradients, you pull things up onto the double cover in this combinatorial way, and you glue things together. By following the exact same procedure, except by using the WKB filtrations, you actually get that defines a functor. That defines a functor now between these categories of H-bar connections. So maybe the last thing I'll say is about the cocycle. So what about the cocycle? Well, if I again repeat the same procedure by, now I've constructed my line bundle L with an H-bar connection. I push that forward. Now I get two rank 2 H-bar connections downstairs. I compare them in the exact same way using all these canonical identifications over diamonds. That gives me a cocycle, which of course necessarily depends on H-bar. And so what turns out is that this cocycle is first of all is holomorphic in H-bar, simply because all the filtrations and all the steps that I did, everything is holomorphic in H-bar in this sectorial domain, and they admit correct asymptotics. So they have an asymptotic expansion in this half plane in the direction theta. And then like the last clincher is that if you look at the way this cocycle is defined in terms of the parallel transport of the abelian connection, and the fact that the abelian connection has this leading order part, which is the canonical one form, all of that together, you do the calculation and you see that this cocycle in the limit as H-bar goes to 0 just becomes trivial. So somehow this is I kind of like this, because although I've put the I'm using the Stokes graph in order to abelianize my H-bar connection, but the Stokes graph it lives for all H-bar, including H-bar equal to 0. I mean, in fact, that's where I built my Stokes graph. It's in this central fiber, and then I just extended it in this stupid way. So so you could say, how come it doesn't, like what does the Stokes graph do at H-bar equal to 0? It's sitting there. Why doesn't it affect the Higgs field in any way? And the answer is that, well, actually what affects my construction is the cocycle that encodes the Stokes graph. And the cocycle becomes trivial over the central fiber. Okay, so I think I will stop that. Thank you very much for your attention.
Thank you very much. I think we have a couple of minutes for a question before the break.
Hello. I saw that in your work you make crucial use of the poles of the meromorphic, of the original rank 2 meromorphic connections. But can we do something if there's no pole?
Yes. So yeah, so this is kind of a very recent thing that I think. So this result about these where is it, the WKB filtrations. So yeah, I mean I originally proved it when I have poles, but then I realized that I think the proof kind of goes through when you don't have poles. You just have to, your Stokes graph has to be of a of this particular shape. I don't know if the word makes sense for you. It has to be a Strabel differential. And then you have these closed kind of ring domains. And I think in the ring domains, I think this basically the same theorem holds, well, minus the 0.2 because there are no Levelt filtrations. I still need to, write it down and check it, but I think it works. And so I would be able to do it in the case where there are no poles.
Yeah, but what actually, like, for example, if we have a pole, then we can define the filtration according to the growth rate. But if we have no pole, how do we even start to define a filtration? Because that's to abelianize, to pick out a subline bundle.
Right. Well, you see, the one of the points in this theorem, I guess, is that the point about growth rates is really just here. It's 0.2. It's somehow it's a feature of these filtrations rather than a defining property. So when you have poles, this theorem says that you have these canonical filtrations and they have properties. One of the properties is that you restrict it near a pole and it coincides with the Levelt filtration. But that's just that's a feature which happens in the presence of poles. And if you don't have poles, you don't have that feature, but the filtrations still exist.
I see. Okay, so it's not the level of filtration anymore, but
Correct. Yeah. By the way, who is speaking? I couldn't say.
I'm Zoom.
Okay.
Yes,
Nice to meet
we
you.
met before in the Windows school, but maybe
I see.
Maybe a minor question when you say that we right. I mean, for example, for the Higgs bundle case, if you want to do the push forward construction to recover the original Higgs bundle, we actually need to, tensor with some power of the canonical bundle and so on. And is there something similar here when you construct the inverse of the non-Abelianization function?
Right. So this this thing about tensoring, yes. So I deliberately did not say this, but so this statement is on the nose, correct? So there's two ways of doing this spectral correspondence. One, which is what you're suggesting, which you define your spectral line bundle precisely in this way as the kernel of this endomorphism. But then it indeed turns out that if you take this line bundle L and you push that forward, then the push forward is not quite E. You need to twist it by indeed a push forward of something else. But then there's another way of constructing it, which is that you twist, you take this line bundle L, you take this line bundle on the spectral curve, and you twist that at ramification. So then it becomes kind of it's defined like this, but up to a certain modification along the ramification locus on sigma. And if you define L that way, then you get this equality on the nose. So either upstairs or downstairs, you need to do a certain modification.
Yes.
But I always choose to do it upstairs.
Yes, and that will also occur for your.
Yes, in a way, yeah. So when you extend, yeah. So when you extend the Abelianization connection over the ramification locus, there's an argument that you need to do in order to get a canonical extension, and that. I mean, it's not the same as twisting by what you get in the Higgs bundle case, but it kind of feels the same.
Okay. Thank you. Thank you.
So I also have a bit of a question, which I'm not sure whether it's trivial or very hard. You're doing this in rank 2. What if you increase the rank?
Yeah, well, I guess that's a £1 million question. But
okay,
yeah,
so very hard then.
It's I actually have that's work in progress with Marco Gualtieri, and I think the key, at least from this point of view, the key new ingredient is a certain auxiliary curve. So you see here, I always have X, and I always have the spectral curve sigma. And those are somehow the two main players, nothing else. But actually, there's an additional curve when you go to higher rank. There's an additional curve that you need to construct. The construction is canonical, so it's not really any new choices. But you need to use that auxiliary curve in order to basically build this cocycle. Where is it? V, somewhere down the line. This cocycle V, well, I've lost it now. You need to introduce that auxiliary curve, and that kind of helps you. So, I mean, one of the main reasons why it's so difficult when you go to higher rank is because the Stokes graph is really crazy, and the purpose of that curve is to remove this insanity. So actually, on that curve, the way I gave you this definition, and there's an extra reason why I like this definition, because when I go to higher rank, then if I transfer all the action to that auxiliary curve, then the definition of the Stokes graph is exactly as you see it now. It's precisely the same. So that's very very attractive to me. And then I can basically use this whole, I repeat this entire structure of all these diamonds and, the way I assign the cocycle, et cetera, et cetera, et cetera. But there's a kind of a couple of things in that construction which I'm still, well, I just need to maybe sit down and try to think about them very, very hard. Maybe like lock my door for a couple of days and just not come out until I come up with something useful. Yeah.
Right. So the main reason I'm asking this is that like, spectral curves always remind me of topological recursion, of course.
Oh yeah.
And then if you assume that the spectral curve still has simple ramification, then maybe you should be able to do something locally around these ramification points. I'm not quite sure, but lots of parts of your story seem like they could be related.
It's a hidden agenda of mine to understand topological recursion from this point of view, and I think there's a lot to say. But I don't have anything intelligent to say at the moment.
Okay, well, same, but I also agree that there should be a lot to say here somehow.
Okay, thanks very much, Nikita. And I suggest that if you want to discuss further, maybe we discuss during the break. So thank you, Nikita. And
Thanks.
we'll resume with the next talk in 15 minutes.
Thanks a lot.